big goal of mine is to examine efficient and non-invasive means of producing tangible replicas or casts and three-dimensional files of vertebrate fossils using 3D imaging techniques. The traditional production of injection molded casts is laborious and pretty time-consuming, and it often takes several attempts and a lot of wasted material to produce research quality examples. So here I've opened a program called Netfabb. It's a free CAD software you can download on the internet, and this software is good for looking at a model. You can spin the model, you can examine the model for flaws that might impede the printing process. So the first thing you need to do is grab yourself a NextEngine laser texture scanner, and from there a raw STL file. STL stands for stereolithography. In this case, I am going to import a mesh representing a juvenile Tyrannosaurus rex dentary. So let's see, I'm going to find the file. We'll use the right dentary. We can see off the bat from spinning this around that there are some flaws in this mesh. So I go close, and these black spaces here, these are holes in the model. So if I were to actually cut this up for printing, these areas would not print, and I'd end up with an unstable model and an unsolid model. So it'd only print the outer layer. A point cloud is essentially a set of points in a three-dimensional XYZ coordinate system, and they represent the external surface of the object. 3D scanners create point clouds by measuring automatically a large number of points on the outside of the surface. The points are then joined to create a mesh. You can move your cursor right over to this button here, click that, and now use your fingers to zoom in on the object. You can see each one of the points that the scanner actually detected on the lower jaw. To actually repair this model, I'm going to use another program called Netfabb. You can go online and download it. It offers a variety of functions to view, handle, edit, and repair three-dimensional files. These functions serve as preparation of virtual objects for 3D printing, rapid prototyping, and additive manufacturing, including all process steps from three-dimensional CAD to the actual manufacturing with a 3D printer. It's a pretty easy software to use. It has some functions that I don't even know about yet. I'm not sure what other Netfabb tutorials actually use to repair models, but I'm going to show you the process that works best for me. So first I have to go in and open my file. So I'm going to use the dentary STL. Here we are. So Netfabb fixes your object in space. You can't rotate it like you would in Netfabb. Instead, we have these functions to view the top of the model, the bottom of the model. We also have lateral views, left and right, front, even sort of from the corner. I find it best to have a head-on view like this, because what needs to happen is I need to slice this into various sections so that they'll fit in my 3D printer. If I slice them as is, it's not going to work, because I already showed you in Netfabb that we have some open spaces in this model. So to fix these open spaces, I'm going to go under the Extras menu and choose the Repair Part option. And what you can click is this button that says Automatic Repair. It's safer, I'd say, to go with the default repair. What it's going to do is fill in the missing gaps in this model and turn it into a solid 3D printable piece. This repair took roughly 20 minutes to complete. First, examine the repaired object from different views to determine that the program did not vectorize areas that represent the morphology of your specimen. So we're going to look at it from the corner. And you can see, as I approach the point cloud, that it's now stitched the open areas, and it's turned that into a solid mesh. Then we'll look at it from another angle, and I'm just checking to make sure it did not place vectors anywhere where I would not like to see them. It's actually done that in a few places. You can see right where I'm dragging my mouse, it's added vectors to the open space, but I am not going to worry about that in this case because it is a minor error. So once you're finished with that, select Apply Repair option in the corner, and then remove the previous mesh. So remove old part, yes. And so now you can see your finished part. So now the model must be sliced so that it can fit within the bed dimensions of your printer. Netfabb can prepare simple cuts parallel to 3 main planes. That's an X, Y, and Z axis. We can illustrate and preview the result of a potential cut without actually performing it. So I click X-axis, and I can drag a cutting plane across the X-axis. I click Y, and I can drag a cutting plane across the Y-axis. So to fit within the dimensions of my printer, I don't want to be much more than about 110 millimeters right here. So once you're properly positioned, execute the cut, and you'll be left with 2 separate meshes, one of which is ready to be imported into 3D printing software. So execute cut, triangulate cuts. So here's the new part. What I like to do is take the old part and actually remove that. And now I'm going to focus on this guy. I'll click Repair Part, and it's going to seal up that edge that I just cut. I don't think I did that right. Automatic repair, execute, apply, remove, yes. We're going to go under Part, Export Part, we'll export it as an STL, and we'll save the file. It's going to add an extra repair before it exports it. So here I'm using UP software, which is produced by the PP3DP Corporation. This software will work for both UP and Affinia 3D printers, but nothing else. That being said, it's very similar to many of the open source options that are currently available free for download on the web. So what I'm going to do is load the model we just produced in Netfabb. And see how well it fits. So you can see it's not immediately in the area of our print bed. To fix that, we select Auto Placement, and can see, if we rotate the object, that it almost fits in the area of our print bed. It's also important that the face of the object that's going to contact the next piece not touch the print bed. So make sure to keep that in the orientation I have it here. To make it fit a little better, we can select this rotate option, and I'm going to rotate it 10 degrees on the Z-axis. So that provides a little more space for the printing. And if I want to move it, for instance, I can select the Move option and move it here, back. Now we can see from looking above that the object fits roughly within the area of our print bed. That being said, we have an option of materials to use. So under 3D Print, select Setup. What we want is a very fine Z resolution, so we'll do 200 micrometers, which is 0.2 millimeters. Also, the software will automatically produce a smart, auto-generated, and easy-to-break-away support material. And this angle here, the support angle, is the angle at which smart support material will get inserted. For example, we have 30 degrees selected. If this is used, the support material will only be used if the angle of the surface is greater than 30 degrees from the horizontal. And I do use 30 degrees when I'm producing these models. This area option here represents the surface area above which support material gets used. The default is usually 5 millimeters squared. I use 10 millimeters squared. The stable option will produce a more stable support. Unfortunately, if you have a very pockmarked surface, as I have with the stenary, the support material will be almost impossible to remove. So I do not select stable. There are 4 types of honeycomb fill that the interior parts of the 3D print will be made out of. I always select the option that says loose, which is a semi-solid honeycomb. This ensures a proper balance of rigidity and resistance to warping during the print cycle. These other options don't matter as much. I choose a space of 12 lines. That's the space between which the support pillars will be produced. And I don't like having a lot of pillars because that increases the chances that your part will warp. So with these defaults selected, what I'll do is go to maintenance, and I'm going to make sure we have enough material. I'm going to select ABS plastic as the material I'm using, and I am loading a new spool of approximately 1,000 grams. You have an option of materials to use, and for replicas of vertebrate fossils, ABS plastic has to be your option. ABS is more flexible than PLA, but has a much higher melting temperature, 270 degrees Celsius, compared to PLA, which can sag over time. And if we want to make scientifically viable casts of fossil specimens, we don't want sagging, because sagging is going to create a false morphology. Now, we can use the software to give us a print preview to make sure the part will actually fit. I have an option to select what quality I want. Quality essentially means how fast the print head will be moving. If I select fast, it's going to get done pretty quick, but I'm going to lose detail. So I always use the fine option because I have plenty of time. And I will select this unsolid model option. That means if you happen to have a random floating vector, the software will be okay with that, and it'll print that. So let's run the preview. Now it's slicing. It has to slice these layers into 200 micron units to be printed. You can see that we have 523 layers here. Alright, so we can in fact print. If it was outside the boundaries of the print area, it would have given us a message. So we will use about 56 grams of plastic in exactly 7 hours to print this object. So then I'm going to go ahead and print. So I want to test the viability of 3D printing fossil remains, and to do that I have a few things in front of me. I have the denary we just printed as part of the tutorial, as well as a cast of a Tyrannosaurus rex tooth prepared using the traditional methods, so silicone rubber and resin. And I also have a juvenile Tyrannosaurus rex tooth from an animal about the size of the one I'm printing. Under the scope, we see that on the fossilized tooth there are several fine details. Most striking of all are the serrations you see at 10x magnification here. Ideally, to be a good cast, you should resolve features like serrations. So on the cast, we see that there are fine serrations even at 10x magnification, so the old methods work. We see under high magnification of the 3D printed piece that there is no real semblance of serrations or finite features like fractures that we see on the real specimen and we also see on the cast produced using traditional methods. So my verdict is that while 3D printing at 200 micrometers cannot yield a scientifically viable replica of a fossil specimen, it can yield an exhibition quality fossil. So theoretically, you could produce an entire skeleton using a 3D printer for less than 1/10 the standard production cost.